Okay, great. Thank you for the nice introduction. Yeah, so you introduced the paper for me, but essentially this is a collaboration with University of Wisconsin-Madison and Microsoft Gray Systems Lab. And we're going to be looking at auto-tuning, which is essentially this general process you can see up here. This is very common to a lot of prior works that we've seen in kind of the famous names of AutoTune, LlamaTune, QTune, CBDTune, and things like this. And so the thing is, not everyone here knows this, so we'll go quickly through what this actually means. Generally, you have some system that you would like to optimize, and this can be a variety of different systems. Some common ones that people like to tune are Postgres, Nginx, and Redis. These are databases or a web server or a key value store. However, we are not limited to tuning these systems. There's actually many types of systems you can tune. You can also tune storage systems and operating systems and things like this. So we'll pick Postgres for our example for how this works. We would like to run some workload that we would like to optimize on this system. And so there's, once again, many different choices for what kinds of workloads you might want to run. So for a database, some common workloads that you might see will be something like TPCC, which is a warehouse that essentially represents and tracks customers that are shipping things to different parts of the world. You have ePinions, which is a customer review site, or the back end of a customer review site, or you have something like Wikipedia. So we'll pick TPCC as the workload that we'd like to run. And then finally, we come to this optimizer section on the bottom left here of the screen, which is going to be suggesting you configurations to try and hopefully improve the performance of this workload running on this system. And so what these things look like is for Postgres, you would have something that changes potentially how long you have something in the buffer before it clears. You might change what algorithms you're allowed to use to go kind of run this system or workload. And so you have other options like number of threads and how big certain buffers are. And finally, we have this last component in the top left where we have a data store where we keep track of how every single configuration has run. And essentially, we're going to go back and look at the end at which configurations performed the best and try and select this for deployment in a production setting. So very quickly going through it in order, we have the optimizer, which suggests configurations. We then move these and deploy them onto a system. We then benchmark this and run the workload, seeing how the system performs. We then store this and feed this back to the optimizer to hopefully give us better and better configurations over time. And eventually, this is going to give you hopefully a wonderful configuration that runs your system perfectly. The problem is that if you want to deploy this in the cloud, these measurements that you're taking of the system are not necessarily actually representative of what this is going to look like in deployment. And the bigger problem is that Bayesian optimization and Gaussian process models, which is frequently what's used for the optimizer, actually expect essentially perfect measurements. And so we want to fix this with our system TUNA, which we're going to be placing in between this kind of optimizer section or the orchestrator section and the worker section on the right. And so using TUNA, we find configurations which perform for up to 47.8% better with 87.8% lower variability. And importantly, we're going to prevent unstable configurations, which we'll introduce what those are in a second. So to kind of define what these problems are, we'll go back to this Postgres example running TPCC. And if we run this tuning setup, we can go and see that we can actually see pretty significant performance improvements in the cloud. We see 8.4 times better in performance than the default configuration. However, there's some problems. If we take the best configurations that we saw and we deploy them to a new set of workers that are identical in terms of hardware specification, and we try and see how these perform on these new workers, we find some problems. So these are 6 sample runs where we took the best configuration and we deployed them, and we see that 3 of them on the left in the green performed actually not very nicely. They have very nice tight variabilities. However, on the other side, on the right, in the orange, we have these configurations that have very large box plots, essentially meaning that we have unpredictable performance. So these configurations on the right, during tuning, looked amazing, but during deployment, they degraded by over 70% in some cases. So in absolute numbers, this is essentially you're going from 3,000 transactions per second to potentially less than the default at 700 transactions per second. Another problem that we see in the cloud, and we simulate this by using a bare metal system running a slightly different workload, which is this website workload. When we run this workload, we find that we can find configurations with 40% better performance, so not as big as this 8.4 times performance improvement. However, if we simulate noise, so we're injecting synthetic noise on a bare metal system to represent this kind of interference pattern that happens in the cloud, we find that convergence is significantly hindered on finding good configurations. So if we have 5% variability or standard deviation, we find that it takes 2.5 times longer to find an equivalent configuration to a system without noise. And if we have only 10% variability, it's taking 4.3 times longer. So one thing that we need to do first, before we actually kind of develop any system, is measure how much variability exists in the cloud. So we ran about a 15 to 16 month study where we sampled 43,000 different VMs across 83 different benchmarks, collecting about 7 million data points, and also kind of two different kinds of virtual machines. So we had these short-lived classes of virtual machines, which is a bulk of these 43,000 VMs, where we initialized the VM, we ran through our suite of 83 benchmarks, we then deallocated the VM and reprovisioned it, kind of allowing us to sample across the entire cluster. And then we had these long-lived VMs where we ensured that there were no migrations or very few migrations, and we let these live for the entire duration of the study to kind of sample how a single node actually experiences the entire lifespan of a long study. So we've open sourced this data set. We'll have this QR code again at the end, but you can, if you're very interested, you can have it here. You can find this on GitHub too. But when we actually look at this data, what we find, which is different from prior work, is that CPU and disk have essentially no variability as compared to about 5 or 10 years ago in the cloud. So the actual coefficient of variance numbers are about 0.3% and about 0.2% for CPU and disk respectively. And this is in large part because the platform has actually improved these components. They've increased the isolation. Generally, these resources are somewhat under-provisioned to kind of ensure, and they very closely track these resources to make sure that you're actually getting exactly what you pay for. Now, the thing is, memory, OS, and cache, on the other hand, kind of actually experience different problems where they have higher variability, where memory has 4.9% coefficient of variance, the OS has 9.8% coefficient of variance, and the cache has, the cache has 14.4% coefficient of variance. And this is in large part because the isolation is not quite as good as it used to be for these they don't actually isolate these components as they do for these CPU and disk resources. So for memory and for cache, this means that they don't really isolate the buses that the data is transferred upon, and for the OS, there's essentially contention to the host OS. So we need to actually kind of solve this problem of variability still. We can't just trust these measurements that we're taking from the cloud. So going back to this traditional auto-tuning setup, we're going to put something in the middle, like we said before. So we kind of get back to this figure where we're putting something in the middle, but now we'll kind of fill in the components that we're going to be adding. So the first thing we want to do is we want to add an outlier detector. And one obvious way that you could actually implement this is by adding essentially more workers that you're going to evaluate. Essentially every single configuration is going to be evaluated on more workers. If you see a very large range, we're going to penalize these configurations to the optimizer. However, this is very, very expensive. I mean, this would actually increase the cost of doing the tuning by orders of magnitude. So keeping this kind of a little bit simpler, we'll kind of compress these and we'll add a scheduler in here. And so the way that this will work is that we will have a kind of hierarchical process where we will evaluate configurations, or many configurations, and we'll take the most promising configurations that we would like to hopefully see do well and run them on a larger set of nodes. And then we'll kind of repeat this process until we have many of these medium budget configurations, and then we will finally evaluate them on the entire cluster that we're using for training. And then to mitigate this problem of noisy measurements, we're going to be adding a noise adjuster model, which will take system metrics that we see during tuning, and we will essentially kind of try and detect the interference and adjust the scores that we report to the optimizer to hopefully reduce the variability in the samples that we see. So going through an example loop, we'll start with the optimizer, and we'll kind of suggest a few configurations. So we'll start with 6 configurations that we suggest. We will then move to the scheduler, which will then kind of decide which VMs we should be deploying these configurations on. We can then run the configurations on these workers, collecting some throughput measurements in this case, and so we'll have some numbers fill in. We'll then go to the outlier detector, and in this case, because we only have one measurement for every single one of these configurations, there's not much we can do. The range is essentially 0 for all these configurations. We can then collect the metrics off of the workers when we ran these configurations and feed this to our noise adjuster model, which once again is trying to kind of calculate the interference that we see for these configurations, and we can get these adjusted scores. And so we can replace the scores that we actually measured with these adjusted scores using the system metrics. Next, we can go to this aggregation policy, which, because once again we only have a single score, we can just take the value that we saw before, and we'll kind of come back to what this means in a second. And then we can put these in the data store, and then finally we go back to the optimizer. And at this point, we now actually have some promising configurations. And so we have configuration 2 and configuration 6, which ran very nicely. They have a 1207 and 1652 transactions per second, so we're trying to maximize this value. So we kind of select these two scores as things that we're curious about and want to rerun. So then we go back to the scheduler, we then schedule these tasks, and now we're going to be running these on two new nodes, essentially nodes that were not previously run on, to kind of sample across the broader cluster and hopefully get some information about whether or not during deployment these configurations will be stable. We then go to the workers again, we collect some new scores, and now we feed these to the outlier detector. And so the way that we do this is we calculate some range, which is relative to the mean. And in this case, we find that configuration 2 is actually very, very stable. It has a very low relative range, while configuration 6 has an incredibly high relative range, around 70%. And so this is actually very concerning, so we don't want to use configuration 6, as during deployment is very likely to experience the same problem. And kind of as in prior work, to penalize the region, we cut all the scores in half. And so we see here that configuration 6 is now penalized extremely harshly, and essentially the optimizer will never suggest configurations in this region again. We can then move to the noise adjuster, which there's some more details in the paper, but generally we try to only adjust configurations that haven't been penalized, and so we can adjust these two new scores in configuration 2, which then finally, we feed to the aggregation policy, which now we can kind of introduce what this means. And so as a last chance effort to remove unstable configurations, we then use the minimum of the score to kind of optimize for the worst case scenario that we saw during deployment, and we find that this actually gives us very good configurations in the end. So here, finally, we kind of penalize all these configurations, and configuration 6 is penalized kind of in twice because it's taken the minimum and it's been halved. We then feed this back to the data store. We then go back to the optimizer, and now we only really have one promising configuration, which we will then run across the entire test cluster. And we'll kind of skip we would just repeat this loop one more time. Essentially, you can envision we would then schedule this on a few workers, we would take some more evaluations, and that would essentially be the end. And we would repeat this process multiple times until we run out of budget, or we essentially have decided we found a good enough configuration for our liking. Now, we can go to the evaluation. So how do we evaluate this? So the way that you actually generally select in both our system and in the traditional setup is you would look at the scores that you report to the optimizer in the data store, and you would try and find the best configuration. So what we do is we do 10 runs for both the traditional setup and on our TUNA setup, and we select the best run and we deploy this on 10 new workers to kind of see what this would look like, or what the kind of distribution of performance might be for the workers that we deploy. And so we can see that here. We take 10 configurations, we deploy them on new workers, and we measure the performance. So starting with looking at just this kind of traditional setup running on Postgres, running TPCC, we evaluate traditional and TUNA at an equal time budget. So we run them for the same amount of time, and we can see that each bar plot here represents one run that we did. And then each point in the bar plot represents a single evaluation essentially on a production deployment. And we also compare this to the default configuration. And immediately you can see that this traditional setup has significantly larger variability than the default configuration, with two of these configurations actually performing worse than the default. And the reason these configurations were selected is because during training, they actually looked like they were at about that bar. So we can see already that there's configurations that are degrading significantly from what we saw during tuning. Now, if we add the runs that we saw in TUNA, every single one of these is representative, essentially, of what we saw during tuning. We have much tighter variability, and we find that compared to traditional tuning, we have 66.5% lower variability, and importantly, we have no regressions from what we saw. And we should note that we do have 3% lower performance, but importantly, you can actually trust this performance, which we find to be extremely important for cloud providers trying to provide a service or a SaaS offering. Now, as a slightly different evaluation, running the same workload, but this time for an equal budget, this means that we're actually running traditional for 80 hours of tuning and TUNA for 8 hours of tuning. But the cost is the same, essentially, because we're using more nodes in TUNA. We find that the problem is actually even worse for traditional tuning. And in large part, this is because traditional tuning is essentially overfitting to the hardware. And in this case, we find that every single configuration has an extremely high variability. We find every single configuration experiences extreme performance. And in this case, we actually are performing better on average than in traditional tuning. And so we see here that while there are 3 box plots that have slightly higher variability, these are well under our threshold for what we would consider an unstable configuration. And importantly, all of these nice ones on the right have very, very tight variability ranges, and actually on average we're doing better. So yeah, we find 87.8% lower variability, we have no regressions, and now we have 9.2% higher performance than compared to a traditional tuning setup. Additionally, we would like to show that this actually works in production. And so this is one workload. It's this MS sales workload. It's like a sales data set from Microsoft. It is a real production workload. And importantly, yes, while there are not actually significantly unstable configurations, we can see here that we're converging significantly faster to stronger configurations because of this distributed setup, as well as this noise reduction model. And so in this case, we find 61.2% lower variability with 47.8% lower runtimes, which is kind of what we're trying to optimize for. So lower is better as compared to traditional sampling. And finally, we would like to show one more system just to show that we're not only working for databases. We use a Redis key value store. There's also an Nginx example in the paper. Importantly for this setup, there's one key distinction. If you look at the bottom here, there's these asterisks underneath a few of these box plots. And so what's happening with these configurations is that there's actually an out-of-memory issue with Redis for this workload, and these configurations are crashing in a few of the examples. So each one has about a 30% chance of crashing during production deployment, as compared to TUNA, which is preventing all these configurations from crashing. So the key contribution here is that TUNA doesn't actually cause any crashing configurations, and we're trying to minimize here, so there is a slightly higher latency, but compared to crashing, we would argue that this is a significantly higher improvement. We would take this 1.7% higher latency. So yeah, thank you for listening to my presentation. You can find the paper there, which is it's pub open source. We have the data set here. And also, if you need a reminder to read the paper, I have some stickers with these 2 fish here if you'd like to talk to me afterwards.